In this video, we solve problem number 1 from the second quiz in the spring 2021 semester in the differential equations class, elementary differential equations at Tulsa Community College. Now, there were multiple forms to this quiz, so not every student saw this problem, but many of the students saw this problem. This problem says, show that the following differential equation is homogeneous polar, and then find an implicit solution to the initial value problem. So we have this differential equation here, and there are 3 ways that you can show that a differential equation is homogeneous polar. Let's briefly go over those, and then we will show how all 3 methods, or at least 2 of the 3 methods, work, and they can demonstrate for us if the differential equation is homogeneous polar. So here's the first method. If the differential equation can be written in this form, m dx plus n dy equals 0, where m and n are homogeneous functions of the same degree, and I will remind you what that is in just a moment. Then the differential equation is homogeneous polar. So that's one option. Now, if we take this differential equation as it's written here, and then we rearrange it so that dy dx is by itself, it could be written in this way. So you might have some function of x and y divided by some function of x and y. If both of these functions are homogeneous functions of the same degree, then the differential equation is homogeneous polar. I hope that you can see that this is just a rearrangement of that. We're just using different names for our functions. Here the functions are named m and n, and here the functions are named f and g. Okay, so that's the second way. These 2 are very much equivalent to each other. So usually when I'm showing that a differential equation is homogeneous polar, I pick one, whichever one of these is most convenient given the form of the differential equation that's stated there. And then the last one is really nice because it's a step in the method. In order to solve the homogeneous polar equation, usually we write the derivative dy over dx as a function. I'll use a different function. If this is f and that's g, I'll call this one h. So it'll be a function of y over x. If you can write the derivative as a function of y over x only, so you don't just have any y's floating around or x's floating around. Every time you see a y or an x, it's grouped like this, as if you're operating on this quotient as opposed to operating on the variables x or y. If the differential equation can be written like this, then the differential equation is homogeneous polar. So any one of those 3 would be fine. I think what I will do is I will verify that this one is satisfied, and then I will show you how this one is also satisfied. So we'll verify 2 and 3, but verifying 2 is the same as verifying method number 1. Because you could multiply both sides of this by dx and then rearrange it, and you could write it like this. Or you can just divide both sides of this equation by x times y, and you'll get that. Any one of those would be fine for demonstrating that this is homogeneous polar. Okay, so first let's write the differential equation in this form, and then we'll verify that the function in the numerator and the function in the denominator are homogeneous functions of the same degree. Okay. So we have that. So if we divide both sides of this equation by x times y, We have y squared minus x squared in the numerator and x times y in the denominator. The top function is what we will label f, and the bottom function is what we will label g. And now we want to verify that f and g are homogeneous functions of the same degree. That requires us to remember this definition. We say that a function of two variables, x and y, is a homogeneous function of degree n if the following is true. If you can replace x with tx and y with ty, and then do some algebraic manipulation and factor out a power of t, and be left with the original function f of x, y, then we say that f is a homogeneous function of degree n. The degree of that homogeneous function is the power of t that's written right here. And when you're dealing with polynomial functions, it's usually really easy to tell if you have a homogeneous function of a certain degree. You just look at the degree of the terms in the polynomials in the numerator and the polynomials in the denominator. That's a degree 2 term because the exponent is 2. That's a degree 2 term because the exponent's 2. So this is a degree 2 polynomial. Since all of the terms are degree 2, this is going to be a homogeneous function of degree 2. Now, with multiple variables, we've got x to the first times y to the first. The degree of that term is just the sum of those two exponents. So this is also a degree 2 polynomial. So we've got not just a degree 2 polynomial, but a homogeneous function of degree 2. So we can kind of already tell that this is going to work, and we should be able to factor out a t squared from everything, but let's actually verify that now. So let's take f of x, y, and replace x with tx and y with ty. And then just do some algebra. If I've got a product and I'm squaring it, I can square each factor separately. We're just using this fact. And then if you look at this term and this term, they have a t squared in common. So that's t squared times y squared minus x squared, and y squared minus x squared is f. So this is t squared times the original function f of x, y. So that means that f is a homogeneous function of degree 2. And it's obvious that that's a homogeneous function of degree 2 as well, but let's verify it. G is x times y. We're going to replace the x with tx. We're going to replace the y with ty. Now you've got two products. You've got t times x and t times x, or t times y. That's the same as t times x times t times y. We can regroup in any way we want, right? Because multiplication is associative. So if we wanted to, we could change the order. That's because of commutativity. T times t is t squared. And you can put the x over there with the y. And then we could sort of regroup. So we're thinking of this as t squared times the quantity xy, and the quantity xy, that's actually g. So since this is true, g is a homogeneous function of degree 2. All right, so this is a homogeneous function of degree 2, so is this. So that means that the differential equation is homogeneous polar. Because they can't just be homogeneous functions, they have to be homogeneous functions of the same degree. And that means the differential equation can be solved with a substitution. That's the first method. For the second method, or actually with our list of 3 methods, the third method, we want to write the differential equation. Let's write the dE as this. dy over dx equals some function, we'll call it h of y divided by x. It could also be x divided by y. Either one would be fine. Before we do that, though, let me outline what we did here. We just showed that f of tx and ty is t to some power times f of x and y. And then we showed the same for g. So we show that g is a homogeneous function of degree 2 as well. And then we had our conclusion here. But since they were homogeneous functions of the same degree, the differential equation was homogeneous polar. All right. So now we've got method number 3. We want to write the differential equation in this way. Now we're almost there. We don't have this written as a function of y over x only yet. But since this is a homogeneous function of degree 2, and this is a homogeneous function of degree 2, all we have to do to write this in this form is divide by x squared. So you're going to divide by x to the nth power, where n is the degree of those homogeneous functions. So in our case, the degree is 2. So we're going to divide everything in the numerator and denominator by x squared and then simplify. When we do, we're going to see that the differential equation can be written like this. So we have dy over dx, or dy dx, equals this expression here. And we're going to divide the numerator by x squared, and we're going to divide the denominator by x squared. We've got y squared over x squared, which can be written as y over x squared. X squared divided by x squared will just be a 1. And then this xy over x squared will reduce to y over x. If you're not sure about the algebra, you should go through and divide every term. That's anything that's that you're adding to each other. So if you're subtracting, adding the opposite and so on, you want to take each of these pieces and you want to divide it by x squared. After you do that and simplify, you should get this. Okay, so now this is a function of y over x only because I've got a y over x squared here minus 1 and a y over x here. There are no y's just by themselves. There are no x's just by themselves. So we have done this. So we divide the numerator and denominator by x squared in order to make that happen. Okay, so from here, now that we have this written in this form, we'll solve this by making the substitution. So whenever you have the differential equation in this form of the derivative equals some function of y over x, you're going to let v equal y divided by x. Then you're going to solve for y. So you'll have y equals v times x, where v is a function of x. Because we're thinking of y as a function of x here. That's what this says. This is the derivative of y with respect to x. It's an ordinary derivative. So y is a function of x. So it's a function of x divided by x. So that's going to be a function of x. So y will be equal to v times x, or x times v if you prefer, where v is a function of x. And then we want to compute dy dx using the product rule. Dy dx is the derivative of the first times the second plus the derivative of the second with respect to x times the first. Let's see. Okay, now that we've done that, we want to write the differential equation in terms of v and x only. So we have this. We have dy dx equals y over x quantity squared minus 1, all divided by y over x. And we want to write this in terms of v and x only. Well, in order to write the differential equation in terms of v and x only, we're going to do this. We're going to replace dy dx with the derivative of the first times the second plus the derivative of the second with respect to x, which is 1 times the first. So dy dx is the same as x times dv dx plus v, and that's equal to v squared minus 1 all divided by v. Now, it doesn't look like it, but every time you do this, this will be a separable differential equation in terms of v and x. So you'll want to separate the variables. That would require subtracting v from both sides. So we'll just have x times dv dx equals v squared minus 1 over v. We're subtracting v from both sides. I'm going to put a 1 in the denominator there. And now we need a common denominator. So the common denominator, least common denominator of v and 1 is just v. So we'll multiply this one by v over v. And then we have v squared minus 1 over v minus v squared over v. And the v squareds reduce. Okay. And now we're here. Now, at this point, once you have this quotient, or excuse me, this product here equals this, we want to take reciprocals. When I say at this point, what I mean is after we have rewritten that right-hand side, this function of v minus v, as a single fraction, we want to flip both sides. We want to take the reciprocal of both sides. The reason for that is that I have a function of x here, and I want it to be multiplied by a dx, and I've got a dx in the denominator. I need the dx to be in the numerator. So I'm thinking of this x as itself over 1. Let's flip that and flip that. In other words, we're taking the reciprocal of both sides. And if we take the reciprocal of that side, that's legal as long as we also take the reciprocal of the other side. So we have a negative v, or v divided by negative 1, or negative v. Then let's multiply both sides by dv. And we have that there. And now we want to, now we've separated the variables. We've got a function of x over here times dx equals a function of v times dv. So we want to anti-differentiate. And then we're almost done. So let's see, what did we do? We separated the variables. That was all of this. And this step from here to here, involved taking the reciprocal of both sides. That's a good idea. We always want to do that. But before we do that, you need a common denominator first. You can't just take the reciprocal of this and the reciprocal of that and subtract them. It's not legal. The algebra just doesn't work out. So we'll say we're going to get a common denominator on the right-hand side. And I'll use RHS for right-hand side. Okay, so we write it as a single fraction. Then we can flip everything, and that's legal, and those are equivalent to each other. Okay, so we separated the variables, then we anti-differentiated each side with respect to the variable on that side. And then once you do that, you have an implicit solution involving v and x. But remember, we want a solution involving y and x. So let's replace v with whatever it was in terms of y and x. So you're going to back substitute. So you're replacing the v with y over x. And if I was just asked for an implicit solution, my v is being replaced by y over x, I square it, plus c, I would leave it alone, and this would be it. This is an implicit solution of the differential equation. Now, we were not just asked for that. Let's see. We were asked to find an implicit solution to the initial value problem. So we need to use this initial condition, which tells us that when x equals 1, y equals the negative square root of 2. We need to use that to find the correct or appropriate value for c. And then once we find c, we need to substitute c back into this implicit solution to have an implicit solution that does not have any arbitrary constants in it. So this is an implicit family of solutions. We're looking for an implicit particular solution. So we have y of 1 equals the negative square root of 2, which just means that when x equals 1, y equals the negative square root of 2. So we can substitute x equals 1 and y equals the negative square root of 2 here. Excuse me. And then see what c would have to be. So natural log of the absolute value of x equals negative 1/2 times y over x squared plus c. X is 1. Y is the negative square root of 2. Natural log of 1 is 0 because e to the 0 power is 1. If I take a negative and I square it, negative times a negative is a positive. Square root of 2 times square root of 2, square root of 4, which is 2. So we have this. And obviously, negative 1/2 times 2 is negative 1. So if we add 1 to both sides, we get that c must be 1. So once you have c equals 1, you have to substitute that back up here, and that's going to give you your implicit particular solution of the initial value problem. So you have natural log of the absolute value of x equals negative 1/2 times y over x squared plus c, where c is 1, so you plug that in. And that is the implicit solution to the, or implicit particular solution. If you prefer, you can call it a PS, to the IVP. Or of the IVP, either way is fine. So we use the IC to find C, making those replacements, replace x with 1 and y with negative square root of 2, solve for C. And then once you have the value of C, you substitute that back into the implicit solution. Okay, great. So that is how we solve this problem. No, again, not all students who took quiz number 2 saw this problem. This is just on one of the forms of quiz number 2. I will post a solution video for the other form of problem 1 from quiz number 2 shortly.